Hello. So here's another video on smart contract security, episode 3 this time, and I would like to talk about integer arithmetic. So in smart contracts we tend to use integers instead of floating point numbers, just because usually the blockchain software doesn't support floating points, and also because it's quite typical to do that in financial applications. Very often we use cents instead of dollars, and then just do away with the comma and the floating points. But anyway, in smart contracts, that's something you have to do with today's technology, and that can cause a number of issues. Also, they are not unique to smart contracts. They keep popping up. So let's have a quick look. So integers can obviously overflow or underflow. They're not usually usually they're always of a limited range, and when they run out of numbers or bits, that they just overflow. That's a bit like the mileage counter in a car. If your car does a lot of miles and reaches the end of what the mileage counter supports, it just flows over to 0 again, and it seems you've done very few kilometers. And that's exactly what can happen with integers. So here's an example of subtraction of two 16-bit integers. These are unsigned integers. Usually you'd use more than 16-bit in a smart contract, but as an example it's easier to put on a slide. So we just subtract 4 from 3, and that underflows, and we get a huge value. We get FFFF, so which is a large number expressed here in hexadecimal, and that's all there is to overflow and underflow. That's what happens, and this you can find this quite often in smart contracts, and in my audits I do come across them quite frequently. So here's a very simple example of code that comes out of an audit I did. This is open source code, which is why I'm able to show it here. So this is an owned smart contract where the owner takes a fee, takes a cut, and there's a cut for the owner and a cut for a charity. And there's this function, a just cut, where the owner can set these. And in order to not to be abusive, this is limited to above 5%, or to a maximum of 5%. This 51 here means that it has to be a maximum. The combined fee has to be 5% or lower. And then the cut is adjusted accordingly. Now, obviously here, there is a require on the total, but there's not a require on the individual parameters. So what you can do here is to have a very large owner cut, close to the maximum range of the unsigned integer here, and a reasonably low charity cut. And as long as the result given for an overflow stays below 51 or below 5%, this code passes. Though the owner can give himself a massive share of this, and depending how the payout code is structured, he could actually, the code could actually just fail, or it could mean he could drain the contract of all funds and take 100% of operations, and that's obviously a way of cheating the user. I think it was unintentional in this case, but it doesn't have to be. Here's an example of this being exploited in the real world. This is a famous case from April last year, and a lot of ERC20 contracts, token contracts, include this batch transfer function, which allows to send a certain amount to a lot of addresses at the same time. And there's an overflow issue in this code, which was exploited in April 2018 for the first time in a project called Beauty Chain. What you can see here, there's an array of addresses and a value. Now, if this value is very large, this multiplication here can overflow. And this means that these require checks can actually pass, because we're checking against the amount which is what we calculate here. So if this is within this range here, if amount is within the range of 0 and the balance of the sender, then this will actually work. And meaning that a huge value can actually be added to the receiver's balance here. And yeah, that's a serious issue, and it was present in a number of ERC20 contracts, probably copied from one project to another, since this is all open source. And it's an example where such an issue has been exploited in the real world, and it's also not that obvious. It's not easy to see. So what other issues do we have with integers? Well, there's obviously a precision problem. If you divide two integers, the result is truncated. Here, this 5 divided by 2 would actually result in 2, not 2.5, because obviously 2.5 does not exist in integers. So in this case, what we can do is to use a multiplier. Divide 50 by 2 and get 25. And this 25 we can use for something like representing 2.5%. Now these things are important, especially when percentages are involved. Usually it's also important to think in which order you do things, because when you calculate percentages, you usually have to divide and multiply. So if you do division first and then multiplication, you get this truncation, and if you divide by an uneven number, you divide an uneven number by 2, or well, whenever there would be a remainder, then you lose precision. And for this reason, you should generally just do multiplications before divisions in these cases. So this brings us to best practices. So obviously there are things that you can do to limit the impact of these things and avoid vulnerabilities. First of all, it's always important to check for overflow and underflows. You need to check the parameters involved and also the operations on them. And an easy way to do that is to use a safe math library, which basically has some built-in checks. There's a really good implementation by OpenZeppelin, but obviously there are others around. Easy way to do it, just to use safe math for all integer operations. And yeah, you should use multipliers to improve precision in case of potential truncations. Basically, whenever there are divisions involved, just multiply everything by whatever number improves your precision sufficiently, and divide the results again. And related to this, just think about the order of operations. Generally, good advice is to do multiplications before divisions, in particular when you're calculating percentages, because that's where you usually divide and multiply at the same time, or closely to each other. And yeah, apart from this, I'll obviously end the video with the same slide as always. You should get your smart contracts audited by a professional. That's all for now. I'll talk about more vulnerabilities soon.